Today, I'm happy to introduce our speaker, Svetlana Meissner, AI trainer, Google Developer Group expert, exactly in this area, artificial intelligence, machine learning. And today will be our last event from session, which I divided by a few weeks, calculus with Python. And today our topic integrals. This session will be not too long. It's not so big topic, but I hope we will find something new from expert, and it's interesting to understand, Svetlana. Is it crucial topic for machine learning developers? Is it so important to have this knowledge, exactly integrals? Uh, in future, will we often use it, or we have any Python libraries which calculate? We don't need to calculate manually. So I stop sharing. If you want, you can share your screen, maybe with any useful resources. And of course, I'd like to get advices. What is best resources to practice with integrals if it's necessary? And
Okay,
I like to
Anna, are you going to show something?
notify.
Anna, are you showing something, or shall I share the screen?
No, I stopped sharing, so you can share your screen.
I can share my screen.
With any resources, materials, with anything you want to share with our AI Math Club.
I'm just checking. Let's just move away. So, I see. Integrals. I just wanted. Okay, can I just explain a little bit and then show how to deal with integrals? Yes, correct. Okay.
Yes, please.
And how do we deal with questions? Are we participant can write questions or ask, or how is usually?
Today, any attendees, any members can have two options. Send a question in chat or unmute microphone and talk. So Maria, hello. Prabal, hello. Feel free. You can unmute microphone and talk, or you can type message on chat.
Okay. Then integrals. So I'm actually not sure how many knowledge you already have. So I just actually speak about my understanding of integrals and show how also you can calculate what to have a little bit, perhaps historically. If you know, we just started perhaps historically, Leibniz, Newton, they started this calculus, the idea, because so here just in this area, it's drawing, it's not perfect, but after that we're going to real models. So the idea was, if we have any kind of function, so I'm writing function, and this axis should be x, this axis y. So, and here we have the function. And integral, as we learn also at school, at college, high school, then we say that integral is actually the area under the function. So the area, I'm writing, so A area, and this area, also if we can imagine the function goes from minus infinity in direction plus infinity, and then you perhaps try to calculate this area. It could be also infinity, but if you're just saying, oh, I'm just calculating perhaps from this point to this point, say we x0, then it could be some value. And now how to calculate this area, the method developed historically. There are many methods. There's the first one was just again idea, just cut this into stripes, so we can really put some stripes here, and then we can approximately calculate the area of this single rectangle, and it could be rectangle. So if you see like this, or we can approximate it every of which rectangle like this, and then also think if you go along with this function, then this point could be perhaps in the middle, or you can also take in the beginning, at the end of this rectangle, and calculate something a middle value. But anyway, so general integral, it's the area under the function. We'll go in a minute to calculate in Python. But they're also very interesting if you think about these small stripes. And I was speaking about Leibniz, Newton, because these calculus started also that you think about the ideas making these very small areas in infinitesimal, and this is also words saying very small. And if you again go in to infinitely small, and then you are calculating also these limits. So the idea of limits, limited small, and then you still adding all these cuts, then you would have the better and better approximation of these areas under the functions. And a very interesting way, if we go also historically later, then you can, still, if you think just area under the function, then you can just think, okay, cutting perhaps not this, still the same, we'll name with this calculation, and then think about possibilities. Now we have this here rectangle. I just put in the random numbers. Perhaps it's also somewhere. Also, we'll say it's somewhere here. It can be one in this rectangle, and we would like to again calculate this area. And now we can use also method like not cutting these small stripes, and this is actually more complicated how to do this. We can just imagine that now we in this whole bigger rectangle putting random numbers, and there are many random numbers. So everywhere we can simulate. Also, computer is the great, also simulating random numbers. And in all this area, we are simulating the random numbers. And then we can just calculate. So again, go on, and this is still the function, f on x. And then we go along this function, so step by step. And in every this step, also decide how big it could be. It could be also very small step, but still concrete step that we decide. And then in the very step, we calculate how many points do we have under these curves in comparison to the points that we generated in all this whole area. And this method is then Monte Carlo integration method is the second method. If you go later to the statistics, then you also can integrate, then completely different from this Newton-Leibniz approach. Then you can really just put like this, throw all these random numbers and just calculate, how many numbers do I have just under the function in comparison to this whole area. This is just completely different thinking about integration with the same idea that we would like just to know this area under the function. So, and now after this complete integration, we go my Also, drawing is a little bit difficult, but I just want to show you. We move now. I'm open to Gemini, and I also asked, so usually to Gemini, please show me examples of integration in Python. It's the easiest way to use Python. Explain how to integrate symbolic and numeric, which libraries to use. And here, what I also showed you, this the earlier approach, we didn't have the computer, so we have to do all per hand, so calculate all these integrals, and that's why we had all the tables later, that if you integrate sine function, it would be cosine function, sine, or like integrating the power function, and then through all these possibilities, we did find the results, so the corresponding other function of integration, and that we are learning also at school or later in the beginning of the college, which functions correspond to specific known function after the integration. And implementation of this in Python, also you need specific libraries. So you here see also symbolic integration. So here in the beginning, we are calling specific function, and it's already this no. So if you integrate this, then you would have also as a result really answer as a function. If you, and let's see, so here we are first integrating, so symbolically we define these symbolic variables and put in, so it's this example. So let's go to the example of symbolic integration with SymPy. So integrate indefinite integral, and also one, before I just showed the function that starts somewhere in minus infinity, goes to plus infinity, and this is an indefinite integral that you are not setting the boundaries. So we are integrating from this point to this point. It's defined integral, and undefined integral, it's without setting these boundaries. And here, so example, we have this specific function. It's combination of two terms. One is x power 2, so power term, and one is this sine function, sine x. So it's the sum of these two terms. And then to integrate, and we just write import SymPy. Oh, can still make a little bit bigger here, so that you also would here have better scaling. So then importing the libraries, define symbolic variables, so x, SymPy, symbolics, so x, this is how we define symbolic variables in Python. And it's again, the procedure is the same, and depending on language, you just have to know which libraries to use and how to define symbolic libraries. Some of you perhaps used MATLAB. They are a little bit differently, but the just different name, but the procedure is the same. You have to know which libraries to import, then define symbolic variables, then you just define the function. Here's the function, so x power 2, and for sine function in Python, then we define this SymPy sine x function, and then we perform these integrations. So we are calling the function just integrate. So SymPy integrate, we're saying which function we have to integrate and over which variables. So here we define f and x, and just printing this. And to see here also we see the results. Let's go straight to Colab. Then I also here just put it this straight, okay, bigger, in Colab, copy this, and so the code you can then run in Colab, import. Here we see define the function. perform integration, the results. So the function to integrate here after running the code, and the indefinite integral x power 3 divided by 3 and minus cosine x. So we see automatically the integral of this power function and integral with trigonometric with sine function. So integral of sine function minus cosine function. So the idea, I'll go a little bit. So here, also correct result. Here was suggested by Gemini. We did this. And here, this definite integral. Let's find the different integral. And now we're having this very interesting function, a power minus x. So here, and now we're integrating from 0 to infinity. And here's also, if you just look at the picture, if you imagine how this a power minus 6 look like. Anyway, it should go by infinity somehow to the 0, so that this area should have these definite numbers. So if you just also try to integrate any function that goes also to infinity, then you just would have the infinity, so be big. But this kind of function that goes to 0 could have some specific value. And here again, just this code example, we can again just take this example, just I'm copying, then I'm just adding the new cell. So putting this, now this piece of code here, now let's run here to get an importing SymPy, define the function, performing the integration, and here performing this integrate. Now we're seeing this, so G, this is the function. Then we're seeing still we're integrating over X, but now we're integrating from 0, and we are integrating, this is also in SymPy infinity. This is how infinity look like. So dot, very interesting sign for infinity. Look like infinity here. And then we have results, the function to integrate, the definitive integral from 0 to infinity is 1. Okay, I just go here because we don't see just a little bit that we see how we are writing these. So if we have f on x, and now we want to integrate, we are using this very interesting symbol. So you can also ask about the history of the symbols, is where it's coming from, but it's a little bit slow. But if you're making this shorter, perhaps it look like S, and S is like sum, or some, that's better, just sum. And sum is also in mathematics, it's look like is this sigma from Greek, it's a sigma, also this, and sigma is this again the sum, and that was where we were summing, calculated the sum of these very small areas, and also from these calculating very, very small areas with sum, then we come after that to these pairs integral. And what we were calculating from 0 to infinity, and putting from 1 to 1 this function, and then we're writing this dx, so how it look like. And then the result would be that we're using then bigger f. So also just how we decide. So we decide just for integrating smaller f, we just writing this bigger f, and we are using also this line, and we are seeing this is from here to here, and this means that in the end what we are so after calculating infinite integral, then we are using this big F and put in big F at plus infinity. Just a moment. I'll got this, and then we can see, and minus this big F at the point 0. So after calculating this infinite integral, then we are putting into this function this from what to what we're integrating, and so we get the results. And then the results. So here that we see that for this specific integration, we just had here this one. Calculate. Here we're calculating. The result is 1. So then go back to Gemini, because we asked about symbolic integration and the other. So here's also one example, more complex function. So it's still, we have here this example of the function. The same import library, define these symbolic variables, define this now h function, and then integral, define that we calculate an integral and write in the results. Okay, we'll take also this one, calculate here, run the program. And we see it would be interesting to see how quickly it's calculated, but it's now it's really in the moment. And here we see the indefinite integral is r tan x, r tan against x, and definite integral from 0 to 1. We are setting then into this function. So r tangent is at 1 minus r tangent is at 0, and the result is pi over 4. Oh, okay. It's the time is running really quickly. Just because we were still integrating this symbolically. Let's check numerical integration. And numerical integration, so because this function or that we have find the way to how to calculate, also using this infinity, so sum, calculating and receiving the function. But the more complex we see at our world, the more complex function we are trying to simulate and then integrate, we don't have these symbolic solutions. And then we go to these numeric solutions where we also, depending on libraries which we use or how this implemented, it's mostly again decided whether it's different method, again, how to cut this in these stripes, or where on the top we decided in the beginning and the end, perhaps to take some middle, or how, again, cut these stripes. So again, different methods that are implemented in the numeric integration, and also possible this other additional Monte Carlo integration, just throwing these random numbers. So you see, numerically, always able to calculate something. Some area is, if this area is so possible, under the curve. Here also we see different functions, and let's copy this example, and we'll see a little bit how to integrate. So here, then we run. We are importing this SciPy from this library as pi, and NumPy as NumPy. So importing these two libraries. Then we are using define the function. We defining this function using here again using sine with from the NumPy library. So and here just defining the function and then performing the integration. So result arrows, calling these libraries, and again we want to integrate this function from 0 to pi, and here as a in the end as a result, so the function to integrate. So really complex. Now we are multiplying x squared times sine x, and then we don't have any so specific one. As a result, we are hitting these numbers. This is the area under this function that we've got to integrate. And here estimated arrow also, that because we are calculating something numerically, we need to also be able to estimate our error by integration. And actually, why we're doing all this? Because we are still or would like to solve the differential equation. So we are also describe our world more and more with different types of differential equations, and the result, how we find the solution for this differential equation, is through the integration. So having differential equation, then using this whole area of integration, the possibility, and we are able to solve this differential equation through also different method, one of, if it's possible, through this integration, and then we would have the solution for our describing of the world, simulating of the processes that we are going to describe. So now we have in case we have some questions, Anna, we can decide.
No, we haven't questions, but I'm happy that we still have ready libraries. My lovely libraries, I still can use with integrals also. So it's super important to understand that I still in integrals area, I don't need to calculate something manually. I still can use libraries.
Yeah, you just have to know which one. Don't know, you can ask Jimmy, always help you to learn something which newer libraries, and it's always also in in movement. So the better calculations method are coming, and it still was just one dimensions that I showed you. The more complex, so if it just function of one variable, it would be area under the function. If you go to two variables, it would be already not area but the space, and going in many dimensions, and then you can the result of integration would be this some object in these many dimensions. Yeah, and then so you need computer to do this for you. But still, the idea, if you have something, so the function or then perhaps plane in 3 dimensions, and or in 4 dimensions you would have something the 3 dimensions, so a little 1 dimension, and if you integrate, then you would have object that is under this curve, under this space, or under under this, and these again the purpose in the end to solve differential equations. So again, d also that we were using there, this is differentiate, and integral is this process. So the how to say, the backwards process to do something. Also, perhaps back propagation, if you go into neural networks, they're a little bit different, but here is also the in machine learning is also, or if you're thinking about the games especially, and you are simulating physical worlds, and then in the game, in real time, you try to simulate all this, some stone falling down, or the water in a river, and so in real time, so calculating. Then you also can think about how to do this, how to again solve in all these points differential equation through integration. So they are very, very big implementation area. But really, how to do this, it's depend how quickly you want to do. Perhaps the easiest way for specific function, better to use this approach, for other perhaps other approach, and then you just again trying to find the better way for the specific problem that you are solving. Okay.
So I can stop recording.